We are Group 10 and we are going to present a design of a shaking mobile in CFD. The industry requires different chemical processes in order to carry out their respective achievements. One of the most important ones is the mixing of substances to obtain a solution. To do this, agitation must be applied to force a fluid through mechanical means to achieve a circulatory movement in the inside of a tank. The success of this process depends on the geometry and therefore on the design of the impeller used. For many years, the design was based on the power required, the cut that is made in the fluid, the pumping, and the time of mixing and flow patterns. This information was taken with experimental data. Nowadays, computational fluid dynamics allow to make predictions of flow patterns without spending money and time in the construction of an equipment without knowing its behavior first. On the other hand, steerers are divided into groups. The first are axial flow impellers, and they generate a current parallel to the one of the impeller shaft. The second ones are radial flow impellers, and they generate currents in a tangential radial direction. For these ones, the most important variable to consider is the shear rate. On the other hand, our type is an inline dynamic mixer. These ones are suitable to increase mixing intensity compared to the static mixers. The bottom of the tank is rounded to eliminate corners and regions where there are no fluid currents. The Rushton turbine allows an obtaining shear rate of 21 per second. It is effective low concentrations of low gases and immiscible liquids. It generates high shear stresses to break bubbles or drops. The objective of this project is to design an impeller and evaluate it through CFD to obtain a shear rate and a power curve higher than the Rushton turbine. The procedure carried out for the project is shown below: simulation of the Rushton type mobile, simulation of the new design, and comparison between the two mobiles. With the help of the CAD Inventor program, a new proposal was made to identify which design could be better. Both designs were imported into Star CCM Plus program, from which certain models were estimated for meshing and physical models to be able to observe the behavior of both mobiles. This was done in order to obtain all the information required to be able to analyze and conclude on which would be the best design. In the following images, you can see the measurements of the geometry of the impeller. The measurements of the pallets and the distance between each pallet are the same, so the values of that measurements from the new pallet still does not exceed the restriction given for this new design. Our meshing assumptions are the following. Polyhedral dual measure is used to have a better geometry capture, more accurate phase flux calculation, and a more homogeneous mesh. Prism layer measure should be used to resolve flow boundary layers, but it is not needed at flow boundary or in solids. We also used a surface remeasure. Moving a reference frame allows studying the behavior of the steerer in steady state. All-way plus treatment is designed to give accurate results if the near wall centroid is in the viscous sublayer, the longer region, or the buffer layer. There is also the constant density because the model fluid is water, where a constant temperature is assumed at which it remains liquid. The density is taken constant. In addition, the cell quality remediation, gradients, and gravity for greater precision, efficiency, and robustness on the mesh. The omega turbulence predicts very well the closed walls. On the other hand, we have the Reynolds average neighbor stocks, assuming no change in time on the model of the entire spectrum of turbulence scales. This decreases the accuracy of the result, but it has a lower cost. The segregated flow was used because it applies a flow equation to each component of the velocity and pressure. The SST K omega is a good alternative to the standard Spalatal-Maras turbulence model for external flows. But what is it? It is a one-equation model that solves model transfer equations for the kinematic eddy turbulent viscosity. The static condition implies that there will be no accumulation in the equipment. Finally, the turbulence suppression model allows to have a better coverage of the different regimes used in the project, since it will be not only work with a turbulent regime, it will also work with regimes that are in transition and others in a laminar zone. The results obtained from Part 1 and Part 2 will be compared. Table 1 and 2 show the results obtained from the simulation. The angular velocity was calculated using the Reynolds number and the physical characteristics of water. Both tables present the same angular velocity because the diameter used was the same. The rest of values were obtained with the simulations. The scenes and animations were performed at Reynolds number of 10,000 and implicitly unsteady. This was the final mesh together with the number of cells obtained for each design. Taking into account the cell quality and the number of cells obtained for each design, it can be said that the quality of the mesh is adequate for both designs. In almost every part of the impeller, there are values less than 5 for the Y+. This implies fluid, which is governed by the viscous sublayer. As shown on the wall Y+ scenes, the Y+ is higher on the paddles of the impeller as expected because they are the ones moving the fluid. It is recommended to increase the number of prism layers so the Y+ could decrease. This value is greater than 5, which involves a buffer sublayer where the range of Y+ must be between 5 and 30. The average of Y+ in both cases is less than 5, so the fluid is dominated by the viscous effect. As shown on the following scenes and animations, as expected for a turbulent flow, the mixture level is higher around the impeller and the turbulent diffusion is responsible for the mixing. In the Rushton's streamlined animation, the impeller produces a soft agitation, therefore the velocity outside the rotating volume is almost zero. On the other hand, the new design is similar to a Smith turbine because of the curvature of the paddles as shown on the animations. In comparison to the Rushton design, this impeller works as expected because it disperses more fluid because of the paddles form. On the velocity vectors animations, it is also shown that the flow is not being ejected radially to the walls of the tank as expected. This means that the impeller is not mixing properly the fluid. In order to increase the velocity inside the rest of the tank, it is necessary to add deflector plates, which are necessary for high speed and for improving the performance for both impellers. In order to improve the design, adding baffles inside the tank for radial impellers as shown on the figure extracted from Unit Operations class ebook steering and mixing, and with a theoretical calculated power of 4.5, the figure shows that 4 baffles must be added inside the tank in order to increase the level of mixture, the radial ejected flow, and the velocity in the whole tank. A good representation of the curve power number versus Reynolds for the Rushton turbine is the one presented on the screen. Especially, we will look at the blue line that represents the Rushton agitator. The data that came out of the two simulations for both Rushton CFD and our own design are shown below and will be analyzed in detail. When creating a chart in Excel with a logarithmic scale, it may be better to appreciate the differences between the smaller values that cannot be clearly visualized with the arithmetic scale. Presenting data using a logarithmic scale is useful when the data covers a wide range of values because it reduces to a more manageable range. Now this scale was used in our graph to get a better approximation to the data. So it can be noticed that the results of our CFD Rushton for the first two Reynolds values 1 and 10 are inconsistent with what we would give in the literature. Moreover, it does not even come close, so we will ignore these values. This can be explained because in laminar regime everything goes too slow, so the solver cannot differentiate the torque movement well, giving it negative values. On the other hand, when we start the transient regime, it can be seen that our CFD is very similar to what it gives in the literature. It has the same behavior in the regimes and in the power number. Analyzing the results, we have a behavior very similar to the literature, which is a good sign. Therefore, we can say that these results are reliable. Finally, we see how CFDs end up in a very similar range, if not the same. This means that both simulations are reliable. We can see that our own design makes it easier to obtain a power number values for a very low Reynolds number, not like the CFD of the Rushton. Another important value to analyze the performance of our design is a power index. From this, we can have an estimate of the agitation intensity of the mixer. The power index was calculated dividing the power reported by the simulations by the mixing value. It can be seen in the graph that the new design has a higher power index than the Rushton turbine, especially when working in the turbulent regimes. This higher power index indicates that our fluid receives a higher speed from the impeller and therefore will achieve a homogeneous mixture in a shorter time. The shear rate is the rate at which fluid layers move past each other. It is determined by the speed of the flow and the geometry. The new turbine design is also superior to the Rushton when it comes to shear rate because its shear rate is larger. The new design works especially well in turbulent fluids. This makes it ideal for mixing emulsions since high shear forces reduce the size of the bubbles in them. Thanks to the higher shear force, vortices are formed that guarantee faster and more uniform mixing than the Rushton turbine. The shear stress produced by our design is slightly higher than the Rushton, so it is not recommended to use our design when working with non-Newtonian fluids, since increasing the shear stress would also increase the viscosity, causing a reduction in the mixing efficiency. This increase in shear stress can help when mixing substances that do not mix naturally, create suspensions, or when making vapor liquid solutions. This type of turbines are frequently used in pharmaceutical, cosmetic, and plastic manufacturing industries. To improve our design of the tank, it would be better to include two impellers. The impeller design is very small using a paddle steerer. The size must be 50 and 80% the diameter of the tank. The study of the mixing is very important to determine the best efficiency possible because an improper design can lead to overconsumption of energy and inefficient processes. Taking into account the characteristics given, the impeller design is similar to the Smith turbine, which is effective for dispersing high volumes of gas. It is more effective due to its curved pipe sections. The results obtained were very similar to the ones of the literature. This good comparison indicates the validity of the new model.